Hi everyone. So in this second last video for the whole series of lecture videos on forces, we are going to discuss about the center of gravity and the moment of a force. Essentially, these are simple concepts that I've learned in O level, and for A level, there isn't really a very big difference between the two. But I guess it will do us well for us to have a quick revision over this concept. So for the learning objective, we are going to do D, E, F, and G. So although it may seem that we are satisfying quite a lot of learning objective, this is going to be a simple video, okay, a short and simple video. So now for center of gravity, you should know that the center of gravity of the object is basically the point through which the entire weight of an object may be considered to act. So for example, let's say we have a rectangular object. So for this rectangular object, I can segment it into 4 different segments. In fact, I can even break it down into even smaller particles like its molecules and atoms. So every single 4 segment, okay, or even the molecules itself, they will have their own weight, their own mass, their own Cg. But when I look at it as a whole system, the whole block, the whole system of molecules and segments, essentially, I can also say that the weights of 4W acts at the Cg, where the point the entire weight of the object may be considered to act. The position of the Cg also affects the stability of the object. So in general, the lower the center of gravity, the more stable the object will be. Then finally, for the object, okay, with uniform thickness and density, the Cg is basically at the geometrical center. But for an object that is of non-uniform density and thickness, the Cg can be found by using a variety of methods. One is called the plumb line method. So basically hang the thing and then just draw the plumb line for a few positions, and then the point whereby all the plumb line intersects, that will be the Cg. So now I'm going to show you this video. So this guy is going to show you a method that you can use to find the Cg of an object every single time.
Number 1. Have a friend hold a cane out horizontally for you, or another similar object, and putting your 2 index fingers together, try to place them underneath the center of mass. When they let go, you will find it doesn't normally work. But now try putting each index finger at opposite ends of the cane and then moving your index fingers in towards the middle. What you will find is that they always end up right under the center of mass of the cane. You can try starting off asymmetrically and they will still end up under the center of mass. You can try going at different speeds, really slowly, or really fast. But you still end up perfectly under the center of mass. How does this work?
So this guy basically have a YouTube page called the Veritasium. So if you're interested to find out why, by all means go and visit his YouTube page, go and find this extended version of this video. And at the same time, okay, this guy has a lot of interesting videos about physics and science. So really, his video is really quite interesting. Unlike your tutor here, who is so boring. Anyway, the moment of the force is defined as a product of the force and the perpendicular distance of its lines of action from the pivot or axis. So basically, in equation format, moment of a force is basically the force multiplied by the perpendicular distance from the pivot. So you see that there is this little Greek letter here. It is called tau, T-A-U. Okay, so this Greek letter will be the one that is representing torque or moment. So the word torque also has the same meaning as moment. And then moment and torque are basically vectors, and their SI unit are called the Newton meter. Okay, so let us look at one word example, example 14. So here I have an object that is hinged at one end, and then the distance from the other end to the hinge is basically distance d. So if you imagine that I actually exert a force F vertically downward at the other end, so to calculate the moment is basically the force multiplied by the perpendicular distance. So what is the perpendicular distance? The perpendicular distance is basically distance d. Okay, so how do I actually find that that's the perpendicular distance? Because you must remember perpendicular distance is defined from the hinge to the line of action. So I have the hinge here. So where's my line of action? It will be along the direction at which the force acts. So this being the line of action, this being the hinge, the distance from the hinge to the line of action, 90 degree, that makes d the perpendicular distance from the hinge to the line of action. So essentially, the moment is calculated by just F times D. So I have another example here, same object, but in this case, instead of the force pointing vertically downward, I have the force at a certain angle. Okay, so how do I calculate the moment in this case? So once again, it is really just about the product of the force and the perpendicular distance. So to find the perpendicular distance, I will first extend the line of action. Okay, I'll first extend the line of action. So the extended line of action, and then the distance from the hinge to the line of action. Okay, the point of intersection between this distance from the hinge to the line of action needs to be 90 degree because we are looking for the perpendicular distance. So essentially that's that. Okay, so the perpendicular distance will just be calculated based on a right angle triangle. Okay, d sine theta, in this case the component of the d. So the moment is just the product of force and d sine theta. So let us continue with a new concept called the couple. What exactly is a couple? Okay, the couple is basically a pair of equal and opposite forces whose line of action do not coincide and tends to produce rotation only. So focus on some of the keywords, equal and opposite. So it is a pair of forces that are equal and opposite. So since the forces are equal but opposite, it tells me that F net must be 0. And if there's no net force, it cannot cause an acceleration. So if the object was initially at rest, I do expect, okay, the CG to be at rest at the same time, okay, when this pair of forces acts on the object. But what happens here is that the line of action do not coincide. So end up, okay, the CG will not move, but the object will only rotate, okay. So now the couple, as a summary, does not give rise to a resultant force because they are equal and opposite. But what instead it causes is actually just the turning effect, what we call here as torque. Okay, so basically the torque of a couple is defined as the product of one of the forces of the couple and the perpendicular distance between the line of action of the force. Okay, you may not see that very clearly now, but let us look at one particular example. So here I have an object, I have a couple, basically forces that are equal magnitude, opposite in direction. Okay, the line of action do not coincide. So once again, how do I draw the line of action? Basically, just draw an imaginary line at which the force will be acting parallel to, okay, in the direction of the force. So you can see that I have drawn two line of action for one force, and you can see that even though they're parallel, they will not coincide. So what happens here is the forces are equal in magnitude, opposite in direction. So therefore, I'm sure F net is equals to 0. When F net is equals to 0, it tells me that the CG will not move. So when the CG do not move, what will this cause? It will basically just cause a rotation. So now there is a distance between the force. Okay, the perpendicular distance between the two forces is basically distance d. How do I calculate the torque of the couple? It is basically F times d. The force, one of the force, multiplied by the perpendicular distance d between both the forces. Okay, so that's what I mean in the previous slide. The torque of the couple can be calculated based on the product of one of the force and the perpendicular distance between the two forces. Okay, one last thing, the couple is not an action-reaction pair because they act on the same body. Okay, so now let us look at one example, example 15. So a nut requires a torque of 40 Newton meter to be loosened. If a spanner of 0.20 meter long, calculate the force that must be applied to the end of the spanner in order to loosen it if it's applied at 60 degree to the handle. Okay, so we have the diagram here. So first and foremost, there's method one, we can find the perpendicular distance. So I have a force, okay, at 60 degree from the applied to the handle, okay, 60 degree to the handle. So I extend the line of action, the pivot, okay, have a distance of 0.60 to the point of the force, okay, the point at which the force is acting on, but the perpendicular distance in this case is 0.20 sine 60 degree. So once again, how do we find the perpendicular distance? We extend the line of action of the force. From the pivot, we draw a distance, a perpendicular distance from the pivot to the lines of action. So this is the 90 degree here, okay? And then because we do know that the hypotenuse is 0.20, so using just right angle triangle, we can find that the component of that 0.20, okay, should be 0.20 sine 60 degree. So therefore the torque will simply be equals to the product of the force F and the perpendicular distance 0.20 sine 60 degree. So since we know that the torque required is basically 40, so we can find that the force is actually 230 Newton. So with method 1 discussed, we also have a method 2. So the method 2 is we can resolve force. So if you notice, just now what we are resolving is basically resolving the distance 0.20 into a component that will be perpendicular from the pivot to the line of action. But instead of resolving distance, we can always resolve force. So in this case, my force can be resolved, okay, into a component that is parallel to 0.20, but I can also resolve force into a component that is perpendicular to the 0.20, which is F sine 60 degree. So by resolving force, I can immediately find the moment to be calculated based on this force, F sine 60 degree, and 0.20 meter. So therefore, the torque, okay, 40 meter equals to F sine 60 degree equals multiplied by 0.20. I can find that the force is 230 Newton. So basically both way will work. So sometimes it's easier for us to resolve the force. There will be occasion whereby it may be easier to actually resolve the distance. So look at the question carefully, analyze the question, and then apply the right method to solve that particular question. So let us look at one last example, for example 16. So here we are required to find the moments on a rusty hinge, basically due to the weight of 25 Newton. The hinge, the sign itself, okay, has a length of 1.4 meter, tilted at an angle of 78 degrees. So everything has been drawn here, okay. So in order to find the moments about the hinge, so essentially once again, what we need to do is to extend the line of action of the weight, and find the pivot here, and find the perpendicular distance from the pivot to the line of action. So this should be the 90 degree. So essentially what we need to find is really just the distance d, okay. And then we need to state one assumption. So what's the assumption here? The assumption here is we are probably going to assume the 25 Newton weight is at the center of the sign. The whole sign probably is uniformly distributed. The mass is uniformly distributed. So therefore the length here is going to be 0.7 meter. So to find this distance d, okay, all we need to do is to find the component of the 0.7 that is to that distance d, okay. So essentially the moment due to the weight will be the 25 Newton, okay, 25 Newton weight multiplied by the distance d. So the distance d is essentially 0.7. Where do we get this 0.7? It is the length of the sign from the hinge to the midpoint or the CG of the object. So cosine 78 degree, pressing your calculator, you get 3.64 Newton meter, okay, clockwise direction. So again, the assumption here is that the sign is uniform, thus the weight acts at the middle, okay. So finally, we come to the end of this video. In the next video, we're going to discuss about the equilibrium of rigid bodies. And to be honest, everything that we have done so far since the first video of forces, okay, until now, is really just to prepare to discuss about the equilibrium of rigid bodies. So the next lecture is really the essence of this whole chapter. So please pay attention to that, and then I'll see you in the next lecture. Thank you. Okay, thanks. Bye.